Okay, so let's proceed to the advanced techniques. So from basic techniques or from merely knowing the integration formulas. So let's go to some advanced techniques of integration wherein the basic formula that does not apply first in the given equation. Or for example, the basic process such as the U sub technique does not apply in the integrand. So we need advanced techniques in order for us to be able to solve the equation. So there are four techniques of integration. So we have the algebraic substitution, trigonometric substitution, integration by parts, and integration by partial fraction. So first is we're going to discuss the algebraic substitution for this meeting. Okay, so your algebraic substitution is most likely the same as your U sub, but the aim of your algebraic substitution is for you to be able to create a simpler equation. So the goal of the U sub is for you to be able to reach a certain basic formula, or let's say a formula based format. But for algebraic substitution is you're going to have a simpler form of the equation. But the process is more likely the same as your U sub. So you're going to let your different parts of your integral equation be another variable. Okay, so we're going to introduce a new variable of integration in place of the original variable. So again, it's just the same as your U sub, but they have different objectives. Okay, so substitution is determined by inspection of the integrand. So there are no general rules here, but the skills in your choosing your substitution parts comes only with practice. So that's why, as you have noticed in every topic, I always give you problems to solve so that you'll be able to um, practice the different topics. Okay, so I think the aim of your algebraic substitution in most of the equations that I'm going to present is you'll be eliminating partially the radical expressions. And then, of course, there are other examples wherein you may not totally erase the radical expressions, but of course, we are still be able to reach the final answer. Okay, so let's try to solve the different problems. So as you can see in the 7 problems, most of the problems are um, have radical expressions in the integrand. So most likely we're going to solve this one. So so if you look at the different examples, so these examples can't be merely solved by using U sub technique. So you need advanced techniques in order for you to solve these problems. Okay, so let's start with the first example. So you have the integral of the square root of x dx all over 1 plus x. So again, if we're going to try U sub, okay, so for example, u is equal to um, square root of x. So if we try to get the du, so notice that the derivative of square root of x is 1/2 x to the power of negative 1/2 dx. And notice that in the given equation, so you don't have this term in the equation. So for example, we replaced square root of x with u. Then our du should be this term here. So notice that our du is 1 half x to the power of negative 1 half, or that's 1 all over 2x, 1 over square root of 2x, I mean 1 over 2 square root of x dx, which is not equal to the remaining term in your equation. So meaning we cannot use this u sub technique. So what if we try to use your other term for the u sub? So let's say u is equal to 1 plus x. So getting the dx, so you have du is equal to dx. So you have replaced your 1 plus x as u, then you replace your dx as your du, but your square root of x was not replaced in the process of your u sub technique. So there still remains a term that needs to be replaced. So meaning we cannot use this process again. So that's why if the u sub technique can't be used, because again, the aim of your sub technique is for you to be able to replace every term in the equation. So for example, you cannot solve this one using u sub, so that's the time that you're going to use an advanced technique. So when siya ang inyong, so this is the time that you're going to use the algebraic substitution. So usually in the algebraic substitution technique, so what I teach my class is we usually use the variable z as your algebraic substitution. So we have to use the z variable. So z. Okay, so usually if you come across your radical expressions in your integrand, so usually that's what we eliminate in the process of your algebraic substitution for us to be able to create a much simple equation. So for example, we're going to let z be equal to square root of x. So in u sub, so we directly get the derivative of your u. So that's why we have 1 half x to the power of negative 1 half dx. So in this case, before we try to derive your square root of x, we try to eliminate first the radical expression by, of course, getting the square of both sides. So this becomes z squared is equal to x. All right. And this is the time that we can derive your z and x variables. So this becomes 2z dz equals dx. Okay. So notice that we can replace this term with your z variable. Your dx can be replaced by this term here, 2z dz. And then your 1 plus x. So of course, we can replace your x with z squared, this one. So even though that every term in the equation has not been replaced, but at least every variable has been translated from x to the z variable. All right. So if we try to recreate the equation in its new form, so we have, so square root of x is z, and then dx, so that's 2z dz, and then your denominator is 1 plus z squared. Okay, so trying to simplify it further, so you have 2z squared dz all over 1 plus z squared. Okay, so we can try to factor out your 2 outside the integral symbol. So you have z squared dz all over 1 plus z squared. So notice that from the original equation, and if you compare it in this equation, so I think this simplified version is more tolerable to handle compared with the original equation. So at least in this new format, you can say that you can um, integrate the equation. You can try to integrate the equation, di ba? It's easy for you to see that you can integrate the equation rather than seeing the square root sign earlier. Okay, so next step is, since in the numerator the degree of the equation is in second degree, and the degree in the denominator is also the same as the numerator, second degree, or let's say it's quadratic. So we can use long division. So let's try to use another color for you to appreciate the long division process. So your numerator is your dividend and denominator is your divisor. So that's 1 plus z squared, then divide by z squared. So z squared divided by 1 plus z squared, that's 1. So z squared plus 1 and then minus. So we can go very basic with this one. So denominator is remainder is negative 1. So if you try to write the answer of your division process, that's the quotient plus the remainder. So remainder all over divisor, so minus 1 all over 1 plus z squared. So I hope you remember how to divide algebraic terms and also know how to represent the remainder and the final answer. So writing the new equation from the long division process, so 2 integral of 1 minus 1 all over 1 plus z squared dz. Okay, so if we try to separate the two terms, so that's 2 integral of dz minus 2 integral of 1 all over 1 plus z squared dz. So notice that in the first term, so most likely it gives us the integral of z. So we have 2z. In the second integral, so notice that we have this format. And then if you recall from our previous discussion, from our inverse trigonometric functions, so this format here is more likely the same as your integral of du all over a squared plus u squared. And this gives us the answer of 1 over a arctangent u over a plus c, right? So if you look at the given equation, our a squared is 1, so our a should be 1. Then our u is your z. So getting the final answer, So we have, so let's write it in the upper right. So final answer is 2z. So minus, so 1 over a is just 1 over 1. So that's 2 arc tangent. So u over a, that's z all over 1. So arc tangent z plus c. So this is your final answer. Oops. Okay, so do you have questions for this example? So notice that in our algebraic substitution process, so instead of um, getting the derivative immediately after letting your term be the z variable, so we eliminate first the radical expression before we um, try to derive the z and the x variable. So I think there's an extra step if you compare this one with the u sub technique. So, okay, it's a question. Dire. So here, so long division. So, so it, so from here, from this equation, so I try to make it even more simpler by using long division since the degree of the numerator, the exponent, the degree, is the same as the denominator. So usually you can use long division if the degree in the numerator is higher or equal to the degree in the denominator. So that's how you can. So it's just like dividing a big number by a small number or by an equal portion, diba? So 2 divided by 2, then this one is since they have the same degree, so it can be divided. So for example, the degree in the numerator is in the sixth degree, and then your degree in your denominator is second degree. So you can simplify your equation because the degree in the numerator is higher compared with the denominator, or it may be equal in degree. You can still use long division. Okay. So any more questions? Okay, so I think there's no question. Okay, so let's proceed with the second example. Okay, so this time is we have your integral of 1 all over x minus square root of x. So again, if you try to use u sub, so again, the aim of your u sub is for you to be able to replace every term in the equation and make it into a basic formula. So let's try if you let u be equal to x minus square root of x. So notice that the answer will be its derivative is dx minus 1 half x to the power of negative 1 half. So you can replace this one with the u variable, but your dx is, notice that murag you can't replace it immediately with the u because your dx should have another term of this one. So meaning you cannot use this particular u sub. So for example, if we let u be equal to x, then du is equal to dx. So let's say we can replace this one with x variable, but your and then you, let's say your dx can be replaced with du, but your square root of x was not replaced in the process. So again, you cannot use this u sub technique again. So lastly is, let's say you're going to use u sub in square root of x. So du is equal to 1 half x to the power of negative 1 half dx. So notice that we can replace this one with the u variable, but your dx can't be replaced because your dx should have this term here. And then we have an x variable left in the process of this u sub technique. So again, we cannot use this technique here. So again, as what I have told you, your sub technique comes only with practice. But of course, um, it's not safe to say that in one go you can immediately answer your integral equation. But of course, it you have to go to the process of trial and error method. So you need to try if this particular method works, or so if it doesn't work, you need to try another method. So that's why you need um, a lot of practice for you to be able to see that this particular method will give me the answer right away. So it's not just like, so I think mathematics is not the same as other subjects that you can just scan for a while and then you can answer later on. So I think you need to really practice solving equations. So it's more of a muscle memory or a practice. Okay, so since the u sub technique doesn't work here, so obviously we need to use an advanced technique here. So I just showed you that the u sub doesn't work in this example. Okay, so again in your algebraic substitution technique, so we're going to use the z variable. So again, you're not limited to the z variable. You can use any other variable. So I think in some of the books that I have gone through over the past years, so other books use the variable v. So they're using the v variable. So you can also use that one. Okay, so again, the concept of your algebraic um, substitution is for you to be able to reach a reach a simpler version of the given equation. So instead of this one, so we need to represent it in a different manner, in a simpler version. So we need to eliminate the complicated term, and that's the square root of x. So square root of x. So again, before deriving, so we have an extra step along the process of your algebraic substitution. So we need to eliminate the radical expression. So by squaring both sides, so z squared is equal to x variable. So after eliminating your radical expression, so we can now derive the equation. So we have 2z dz is equal to dx. So notice that your dx can be replaced by 2z dz. Your square root of x can be replaced by your z variable. And then your x variable can be replaced by z squared. So again, notice that every term in the equation, every variable in the equation can be replaced with the new variable z. So writing the new format in the z variable, so dx is equal to 2z dz. So all over, so x minus square root of x. So your x is z squared Then minus square root of x, that's z. Okay, so if we try to factor out the constant, so we have z dz all over z squared minus z. So of course we can still simplify the equation by factoring out one z in the denominator. So 2 integral of z dz all over z times z minus 1. So we can cancel one z. So the final format is 2 integral of dz all over z minus 1. So notice that this one is already the simplest form of the equation. So comparing it with the original. So if you know the shortcut for this one, so usually the answer for this one is ln already, but if you want to verify that it's ln, so we have to use the u sub technique here. So let u be z minus 1. So du, getting its derivative, that will be dz minus 0. So your z minus 1 is replaced by the u parameter. Your dz parameter will be replaced by du. Okay, so you have 2 integral of du all over z. Sorry. Du over u there. So du all over u. So again, this one is a basic formula, so this becomes 2 ln of u plus c. So bringing back the value of the u variable, so we have z minus 1. Then bringing back the value of your z, so the final answer is 2 ln of square root of x minus 1 plus c. Okay, so that's the final answer. So notice again, if you compare the process of the algebraic substitution with the u sub technique, so the main goal for your algebraic substitution is for you to be able to reach a simpler format. So this is the format from the blue one going towards this equation. And then the aim of your u sub is from the simpler equation, representing it in the basic formula. So from the green here, so this one is represented by the basic formula. So of course you can have multiple substitution technique in one integral equation. So as long as you just bring back the equations or the value of your variables that you represented into its original form. All right, so questions? Okay, so let's proceed with the next example. Okay, so next is we have this example in the integral of x cubed. So the 3 here is the exponent of your x variable. It's not the index of your root function. So x cubed times the square root of x minus 4 with respect to x. So again, if we try to use u sub, so of course I'm going to show you the u sub because again, if you're answering it on your own, so you have to to try every method possible for every equation that you encounter. So let's say you're going to let u be equal to x cubed. So du is equal to 3x squared dx. So notice that you can replace this one with the u variable, but your dx, so it should be that you have 3x squared along with dx, but the remaining term here is x minus 4. So meaning you cannot use this term here. So let's say you are going to use du here. Du is equal to, u first. So let's say u is equal to x minus 4. So du is equal to dx. So you can replace the inside of the square root with u, your du with dx, but your x cubed was not replaced with the process of this u sub again. So we cannot utilize this process again. So what if we're going to use the square root of x minus 4? So getting its derivative. So notice that the process of u sub is letting one term be the u and then immediately deriving it afterwards. So 1/2 x minus 4 negative 1/2 dx. So again, it's impossible for us to replace this again with the u terms because not everything can be represented or be replaced in the u variable. So di gyapon siya, di ba? So of course, we're going to use the algebraic substitution method. So z is equal to, so again, it's best that we try to eliminate the radical expression. So of course, not every example that you can encounter maybe you always use the radical expression as your z variable. So it may be in other examples that it could be a binomial only to make matters to make the equation more simpler. So I think in the next example that will be uh, the example for that one. So z is equal to square root of x minus 4. So again, before we try to derive, we have an extra step by eliminating the radical expression. So this becomes z squared. So squaring both sides, we have z squared is equal to x minus 4. Okay, so if we try to get the derivative, so we have derivative. So we have 2z dz is equal to dx. All right. So if we try to represent every term here, so again, this term here is represented by the z variable. So your dx can be represented by 2z dz. Diba? So 2z dz. Sakto ba? Diba? So 2z dz, or let's try to to simplify terms first. So notice that we have an x cube here, an extra x cube variable, and that needs to be replaced. So where do we get the x cube? So notice that in the second line, this line here, so we can isolate the x first. So this becomes z squared plus 4 is equal to x. So meaning we can let this one be the x variable here. Okay, so I think every term in the equation can be replaced already. So in the new format, so x, so since this one is x cubed, so you have z squared plus 4, and then times z, so this one is cubed, so times z, that's from the square root of x minus 4. Then from dx is you have 2z dz. Okay, so simplifying it, so isolating or factoring out the constant term, so 2 integral of z squared plus 4 cube, and then z squared dz. So from this term, so it becomes even more, I think for you it may not be simple, but I think for me it's already simple because we can work this one out since it's only a cubic binomial. And I think you can expand up until cubic, di ba? So expanding your z squared plus 4 first. Okay, so let's try to expand this one first. So you have, so expanding the 2z squared plus 4 first. So you have z to the power of 4 plus 8z squared plus 16, right? Then multiply again by another z squared plus 4. So of course this one, what I'm showing you is the manual way of um, expanding your cubic binomials. So the shortcut version of it is the Pascal's triangle. So Pascal's triangle. So that's another way of expanding your binomials. So expanding this one is we have z to the power of 6 plus 8z to the power of 4 plus 16z squared plus 4z to the power of 4 plus 32z squared plus 64. All right, so in the new format, so that will be integral of z to the power of 6. Then next is the fourth, is the lower degree, so that will be the fourth z to the power of 4. So we have 12, so plus 12 z to the power of 4, then plus 48, 48 ba? Oh, 48 z squared plus 64, then z squared dz. Okay, so next is we distribute z squared inside the equation. So this becomes z to the power of 8 plus 12z to the 6th plus 48z to the 4th plus 64, oops, sorry. Sige, ako lang isuot 64 z squared dz. So notice that you can immediately use the formula, the exponential rule for integrals. So in the first integral, so this will be 2z to the power of 9 all over 9. So plus 24 z to the power of 7 all over 7. So where did I get 24? So notice that we still have a coefficient of 2 outside the integral symbol. So upon integrating each term, so we still have to multiply it by 2. Okay, so plus 96 z to the fifth all over 5 plus 64 times 2, that's 128, di ba? Z cube all over 3 plus c. Okay, so of course, don't forget to bring back the value of the the square root function. Okay, so I think this one is it's long to write. So 2, and then we have a square root of x minus 4, then to the power of 9. Huh? Then plus 24. So 24, then again, square root of x minus 4 to the power of 7 all over 7 plus 96 square root of x minus 4 to the power of 5 all over 5 plus 128 square root of x minus 4 cube all over 3 plus c. So this is your final answer. So if you don't want writing the radical expression, so you may write it in its exponential form. So you may write it in this manner. So 2x minus 4. So instead of to the power of 9, that will be 9 halves all over 9 plus 24 x minus 4, 7 halves, then plus 96 x minus 4, 5 halves, then plus 128 x minus 4, 3 halves all over 3 plus c. So that's another way of writing your final answer. Okay, so questions so far? Okay, so I hope you understand. So I hope you understood the process of your algebraic substitution. Okay, so let's try this example here. So let's try using the algebraic sub in the process immediately. Okay, so if you try to use the the algebraic sub immediately. So again, let's try eliminating first so this will be the fifth root of x plus 1 squared. All right. So if we try to eliminate your radical expression, so this becomes in exponential form, this becomes x plus 1 to the power of 2/5. Diba? So I won't be showing you anymore the u-sub because it's clearly that we cannot use the u-sub technique here. So again, eliminating the radical expression. So this one is radical because it's in the fifth root. So multiplying by 5 halves. So we multiply everything by 5 halves to eliminate the 2/5 on the right side. So this becomes 5 halves. Z to the 5 halves is equal to x plus 1. So nag-guess rin ninyo asa gikan. So again, if we try to eliminate the the exponent here, so we need to multiply everything by 5 halves. So power to power rule. Okay, so after eliminating your um, exponent, so we try to derive. So this becomes 5 over 2 z to the power of, so minus 1, that will be 3 halves dx is equal to dx plus 0. Diba? So notice that here is we can replace this term with the z variable. Our dx can be replaced by 5 halves z to the power of 3 halves dz. So your x variable, so of course I think we can get your x variable in this term here. So let's try to isolate it here. So that will be z to the power of 5 halves minus 1. Diba? Is equal to x. So this one can be represented by z 5 halves minus 1. So notice that every equation can now be replaced by the z variable. So writing the new format, so is equal to, so integral of x, so instead of x, this becomes z to the 5 halves minus 1. And then next is your fifth root of x plus 1 squared. That will be our z parameter. So times z. And then lastly is our dx. That will be 5 halves z to the 3 halves dz. Okay. So if we try to multiply z with this term here, so 1 plus 3 halves, that will be 5 halves. So this becomes z to the power of 5 halves. So let's try to take it step by step. So times 5 halves z to the power of 5 halves dz. Okay, so replacing your 5 halves outside the integral symbol. So this becomes z to the 5 halves minus 1 times z to the 5 halves dz, right? Okay, so next is we multiply or distribute your z 5 halves here. So 5 halves integral of, so 5 halves plus 5 halves, so pila matanan? So 5, di ba? Z to the power of 5. So z to the power of 5 minus z 5 halves dz. So in integrating, so I think it's simple now. So 5z to the 6th all over 12, diba? 2 times 6, that's 12. And then this one is, I think, 5z. So instead of 5 halves, so plus 1. So 7 halves all over 7 halves yapon na plus c. So simplifying it, this becomes 5z to the power of 6, and then 12 minus 10z, 7 halves all over 7 plus c. So I think the tricky part here is replacing your z parameter. So in replacing your z, so since your z is square root of, so atol na siya yana para atong ma-appreciate ang process. So this becomes x plus 1 to fifths, di ba? And then to the power of 6 all over 12 minus, so 10 so kuan din siya dahil 5 over 7 din siya. So this is 5 over 7 because we still have 2 here. So times 2 here. Then times 2 on the denominator because this one is coming from 5 halves. 5 halves, then 5 halves. Okay, so this one should be 5. So 5, and then x plus 1, 7 halves, diba? 2 fifths te. Naglibog, asa ako naglibog sa go. Wait sa. Okay, so x plus 1 to the power of 2 fifths, then to the power of 7 halves, na, all over 7, plus c. So again, that's power to power. So we can, this one is 12, this one is cancel out 2. So the final answer is 5x plus 1 to the power of 12 fifths all over 12, then minus 5x plus 1 raised to 7 fifths all over 7 plus c. So this is the final answer. Oh, pero ma-cancel man ang kuan kay 10 man siya. 10, then 2. Okay. So I think you can verify the examples that I have solved this session in Symbolab. And as per the Symbolab process, so I think the process is different with the process that I am presenting it now. So I think in the Symbolab, ang iyahang usab, I think usub ang iyang gamit, usub. So he let the Symbolab let u be equal to x plus 1. So just try to verify the answer there. But so far the answer is the same, but the process is different. All right. So questions? Okay, so let's proceed to the second to the last example. So we have the integral of x all over a cube root of x plus 1. So usually in my years of teaching integral calculus, so most likely the problems that you're going to use algebraic substitution is the equations having radical expressions. So murag-mura na siya most likely in my experience. So especially on exams, so the algebraic sub can be useful in eliminating radical expressions. So what do I mean by radical expressions? Are those terms having root functions, kana mga cube root, mga square root functions. So that's the radical expressions, or the terms having fractional exponents. So those are considered as radical expressions also. Okay, so if you notice that what we let our z variable be is always the radical term, the radical expression term. So this becomes the cube root of x plus 1. And again, before we try to derive your z variable, so we have to eliminate first the radical expression. So that's an extra step in the algebraic sub compared with the u sub, in which after letting one term be the u variable, so the next step is for you to derive it already. So here is before we try to derive your variable, so we try to eliminate first the radical symbol. So cubing the equation, so this becomes z cube is equal to x plus 1. So next is we try to derive. So this becomes 3z squared dz is equal to dx. So if we try to verify that we can replace every term, so this term here can be replaced by z. Your dx can be replaced by 3z squared. So how about your x variable? So of course we can replace this one by isolating your x. So ang mga x ninyo i-isolate na. So z cubed minus 1 is equal to x. So this one can be represented, your x can be represented by z cubed minus 1. Alright. So in the new format, so again your x variable in the numerator, that's z cubed minus 1. So dx is 3z squared dz all over, so our our cube root of x plus 1 is the z variable. So notice that we can cancel one z. So our equation is even simpler. So let's factor out the constant first, 3. So this becomes z cubed minus 1. And then times z dz. So multiplying or distributing z to each term in the binomial. So this becomes z to the fourth minus z dz. So I think with this basic or with that simple equation, we can integrate immediately. So that will be 3z to the fifth all over 5 minus 3z squared all over 2 plus c. So again, don't forget to bring back the value of your z variable. So this will be, so in my practice, so I like writing the radical terms in the exponential form because I hate seeing kanang mga root functions. So instead of cube root, so I try to write it in this manner. So again, x plus 1, so 5/3. So of course, whichever suits your taste. So of course, I will accept the correct answer gyapon. So it's just my style of writing the, the radical expressions. So 3x plus 1, then 2/3 all over 2 plus c. So this is the final answer. So again, this is my style of writing the radical term. So you can write it in this manner also. Cube root. So murag hassle na siya, di ba? So it's a bit hassle to write cube root of x plus 1 and then to the power of 5. So imagine writing it in this manner. So I think it takes a lot of time. It takes a lot of time writing in this format. X plus 1 squared and murag siya batignaon, di ba? So it's not pleasant to see. So it's also okay to write in this manner. Okay, so questions or clarifications? Okay, so let's go to the potential last example there. So let's go to the sixth example. So let's try to solve this one immediately. So again, eliminating the radical expression. So cube root of x squared plus 4. Then again, before deriving is we eliminate first the radical expression. So that's z cubed is equal to x squared plus 4. So getting the derivative, so we have 3z squared, so derivative 3z squared dz. Then we have 2x dx. All right. So again, verifying first if we can try to replace every term. So this one is the z parameter here. So notice that our dx here has a x variable on its left side. Diba? X dx. So we won't be including 2 because there's no 2 in the given equation. So this becomes 3/2 z squared dz is equal to x dx. So where do we get the extra x in the dx term here? So we need to borrow it from the x cubed in the equation above. So if we try to break it down, so this becomes x squared times x, diba? So this is the x dx that can be represented by 3/2 z squared. Okay, so how about the remaining x squared? So of course, we can replace this one by isolating x squared. So we have z cubed minus 4 is equal to x squared. So of course, we can represent every term in your equation with the z variable. All right. So in the new format, so x squared is z cubed minus 4. So again, we're taking it from x squared first because we have broken down your x cubed into x squared times x because your dx needs the variable, it needs a one variable of x for us to complete the substitution technique. So x dx is 3 halves z squared dz. Then divide by the denominator, that's the z variable. So eliminating one z and then factoring out the constant term. So we have 3 halves integral of z cubed minus 4 then times z dz. So distributing z inside the binomial. So that's z to the fourth minus 4z dz. So base na dz na mo di ano kay puro na ta z. Okay, so we can now integrate. So 3 halves times z to the fifth all over 5 minus 3 halves times 4 times z squared all over 2 plus c. So cancel out 4 because we have also 4 on the denominator, 2 times 2. So 3z to the fifth all over 10 minus 3z squared plus c. So final answer is 3. So again, I'm going to write it in this manner. X squared plus 4 5/3 all over 10 plus 3 x squared plus 4 2/3 plus c. So this is the final answer. Alright, so questions? So no questions. So let's proceed to the last example. Okay, so kani siya is medyo tricky ni siya nga example. It's a tricky example. So again, the aim of your z sub is for you to eliminate all the radical expressions. So for example, we try to eliminate the square root. So you won't be eliminating the cube root, diba? If we let z be equal the cube root function, we won't be eliminating the square root function. Well, so one radical expression will be left behind if we try to represent one radical expression as the z variable. So the technique here is for us to eliminate both in one go. So we'll be eliminating the the square root of x and the cube root of x in one z substitution method or process. So how do we go about that? So for us to be able to eliminate the square root and the cube root, so we need to understand that. So let's say writing it in the exponential form, this will be x to the power of 1/2 The other will be x to the power of 1/3. Okay, so understanding that format, so we need to represent it in one big radical expression that we can eliminate it later. So my style here is I just multiply the exponents. So of course this becomes x to the 1/6. So mag-ana siya. So that so this will be my z function. So if I represent my z as the 6th root of x, okay, so notice that my z becomes z to the power of 6 is equal to x, diba? And then getting the derivative, we have 6z dz, z to the 5th dx. So notice that I can replace your dx with, okay, so my x variable, so again I was not able to eliminate the radical expressions yet, but my x variable is represented by z to the power of 6. Okay, so let's try to observe if I can eliminate the radical expression. Okay, so dx, so let's put that one on top of the numerator. So 6 z to the 5th dz. So square root. So again, my x variable is z to the power of 6. Diba? Then cube root of z to the power of 6. So notice that my z is a perfect square. Diba? Murag, pwede siya ma-represent as z cube times z cube. So 6 z to the 5th dz. So this becomes z cube. And then my cube root of z to the power of 6 becomes z squared. So I have eliminated the radical expression. So again, if for those of you who are confused, ano na mo siyang z cube and z squared. So in exponential form, this is z to the power of 6 all over 2 plus z 6 all over 3. So that's why it became z cubed plus z squared. So that's how you eliminate all the radical expressions in one go. So you need to be creative. So I think this one is a bit advanced, but if you try to solve the equations, I mean more equations relating to this topic, so you'll be able to get the process right away. Okay, so isolating 6 and then factoring out z squared in the denominator. So z to the 5th dz all over z squared z plus 1. So this one is cube. So you have 6 integral of z cube dz all over z plus 1. So again, notice that we have the degree in the numerator is greater than the degree in the denominator. So we can use the long division. So divisor is the denominator, dividend is the numerator. So you have z squared, so z cubed plus z squared, and then minus, so that's negative z squared, then minus z, so minus z squared minus z, So you have z here plus 1, then you have z plus 1, then negative 1. So again, upon representing the final answer, this becomes z squared minus z plus 1 minus the remainder all over the divisor. So this becomes 6 integral of z squared minus z plus 1 minus 1 all over z plus 1 dz. So this becomes, so ako lang i-shortcut because we don't have any more space. So this becomes 2z cubed plus 3z squared plus 6z minus 6 ln of z plus 1 plus c. So of course, don't forget to bring back the value of the z variable. So let's write it down here because there's no more space. So 2, and then so instead of, so let's try to make it even more simple. So there are times that it's easy, it's okay for us to write it on the radical expression. So 6 all over 3, 3 over 6, that's 1/3. So cube root of x minus 3, square root din siya, square root. So then 3 cube root of x plus 6 root of x minus 6 ln of 6 root of x plus 1 plus c. Okay, so this is the final answer. So again, just try to answer the problems again so that you can verify for yourself if the process is correct, or if you have missed, or if I have missed any basic process along the way. All right, so questions or clarifications? All right, so if there's no question, so I'll be uploading the 10 problems in the Canvas course, and then the deadline for which will be next Friday. So again, we won't be having class this Friday, so we'll meet again on Wednesday. But the deadline for your problem set for this topic will be on Friday next week, right? So libog no, libog. Basta we'll meet next Wednesday. So just look for the deadline or the due date for the problem set for this topic in the Canvas course.